In this video, we're continuing our discussion of multiple degree of freedom systems. Here we're going to discuss semi-definite systems. So there are some systems that cannot use the previous techniques without some modifications. These occur when the whole system can move as a rigid object as well as vibrate. These are also known as degenerate or unrestrained systems. Examples of such systems include vibrations of an object in free fall, either temporary or a system in orbit, like a spacecraft, aircraft, trains on a smooth rail line, and other examples. So let's consider a very simple semi-definite system of two rail cars joined on a railway track. So we've got our M1 and our M2 joined together by a spring, and they can be described by coordinates x1 and x2. The free body diagram, mass acceleration diagrams are shown below, or are shown here. So we can write our equations of motion, or use our Newton's laws to get our equations of motion. And what we get in matrix form is M1, 0, 0, M2 for our mass matrix, and then K minus K, K, K for our, or K minus K minus K, K for our stiffness matrix. So when we assume simple simultaneous harmonic motion of the of our usual form, these are the forms of our accelerations, then our system becomes k minus m1 p squared minus k, and k minus m2 p squared times a, our vector a is equal to our zero vector. So for a non-trivial solution, the determinant of our matrix, this matrix, has to be equal to 0. So we get this for our characteristic equation. And this can be expanded and simplified, and we see that we get this equation here. So this equation has roots p1 squared is equal to 0 because of this term, and p2 squared is equal to k times m1 plus m2 over m1 times m2. Now, the zero natural frequency corresponds to a rigid body motion of the system, or a rigid body mode. So to investigate this further, we can consider the mode shapes associated with these frequencies. So from the first equation in 8.31, we find k minus m1 p squared a1 minus k a2 is equal to 0. So we can see that a2 over a1 is equal to k minus m1 p squared over k. So for p1 squared is equal to 0, we get the mode shape 1, 1. If we plug in p squared is equal to 0 here. For p2 squared is equal to k times m1 plus m2 over m1 times m2, we get, we plug in our p squared, and we get that our mode shape is 1 and minus m1 over m2. So the first mode shape corresponds to the rigid body motion of the system. Since both cars are always displaced the same distance in the same direction, there's no stretch in that spring, and the equations of motion simplify to being having zero acceleration. So this has the general solution, x1 of t is equal to at plus b, and x2 of t is equal to ct plus d, where a, b, c, and d are obtained from the initial conditions. So you can see that there is a, we do not have an oscillatory solution here. So there's no vibration in this rigid body mode. So the initial conditions corresponding to the rigid body mode would be x1 of 0 is equal to x2 of 0, so the spring is initially unstretched. And if each car has the same initial velocity. So if the car started with these conditions, they will move as a rigid body at a constant velocity. For the second mode, the masses move with opposite directions, but the same velocity for all times t, if the masses are the same. So if m2 is greater than m1, the amplitude of motion for m1 will be greater than that of m2, and vice versa. In this mode, there will be a spring location that doesn't move, and this point is referred to as a node. So the node is located at a fraction, m2 over m1 plus m2, of the distance along the spring from m1, as shown on the next slide. So this is the vibration mode for the semi-definite system. And we've got, as it's vibrating, there's a point on the spring that actually does not move. So this is a node, and it can be treated actually as a fixed support. Where the natural frequency for each mass is the square root of k times m1 plus m2 over m1 times m2. So if m1 is greater than m2, the node will be closer to m2, and if m2 is greater than m1, the node will be closer to m1. This unmoving node is equivalent to a fixed support, and the system can be interpreted as two single degree of freedom systems, with k effective as we can see here. So we can note that for semi-definite systems, we can't use normal matrix methods because the stiffness matrix is singular, which is always the case for semi-definite systems. A semi-definite system can have at most 6 rigid body modes, which correspond to 3 translations and 3 rotations in 3D space. There are techniques that can be used to remove the rigid body modes, and then we can proceed with some of our usual techniques, but this is beyond the scope of this course.